Finding powers and roots of complex numbers in rectangular form is extremely messy. For instance, if we were to have -1 plus I, and we needed to raise that to the fourth power, in this rectangular form, it would be very difficult because what it means is that we basically have to multiply this out 4 times. So we end up just foiling things over and over and over again, and that's very difficult, and I don't think any of us want to spend our time doing that. Fortunately, a guy named DeMoivre came up with a theorem that once you put a complex number in polar form, it makes it a lot easier. Once it's in polar form, something like 3 cis 30 degrees, if it's raised to a power, say the fourth power, you can simply raise the modulus to the power, so that would be 3 to the fourth, and then multiply the argument or the angle by that power, so that 30 degrees would be multiplied by 4. And of course that makes it a lot simpler to work out. Now you could get 81 cis 160 degrees, and we just did the whole thing in a very, very simple process. So let's use DeMoivre's theorem to work an actual problem. You'll notice this one is given to us in rectangular form, so the first thing we need to do to be able to use anything from DeMoivre's theorem is we need to be able to convert it to polar first. That's the cis form we talked about. So we're going to go -1 plus 1, so it'll end up being somewhere in here in that third quadrant. We can go ahead and draw a triangle. We know this is 1, this is 1, and of course, hopefully, this will come out to a really easy one for you. Hopefully, you recognize this as a 1, 1 square root of 2 triangle. Hopefully, also, you recognize that since the legs are the same, this is a 45-degree angle, which means that the real angle we're worried about is 135 degrees. Of course, you could do this in radians as well. And of course, if you didn't recognize this as a 45-degree angle, you could go ahead and use your sine, cosine, tangent to find those things. Tangent obviously being the easy one. But hopefully, you recognize these really simple triangles. When the legs are the same, you recognize it as your 1, 1 square root of 2 triangle and a 45-degree angle. So we're going to go ahead and write this in polar form, and we're going to use that square root of 2 cis, and we're going to use radians. I think you'll find that these are actually easier in radians because a lot of times certain things cancel out. Of course, this is all raised to the fourth power. So we're going to use DeMoivre's theorem. We're going to multiply the modulus, or excuse me, raise the modulus to the power, and then we're going to multiply the argument by 4. And this is what I mean. A lot of times those denominators end up canceling out. And so you'll see that that will happen in this case. Let's remember what DeMoivre's theorem is. Raise the modulus to the power, multiply the argument. So, square root of 2 raised to the fourth power. That means square root of 2 times square root of 2, which is 2, times square root of 2 times square root of 2, which is another 2. So all of that comes out to 4. Cis, and we're going to go ahead and multiply this. It will cancel out, and we're left with 3 pi. Now, hopefully you recognize 3 pi. That would be pi, 2 pi, 3 pi. Remember, anytime a number is greater than 2 pi, you can just subtract 2 pi from it until it gets to a number that is below 2 pi. So we're left with 4 cis pi as our answer. Now the problem is they gave it to us in rectangular form, so that means we need to give an answer that's in rectangular form. So once again, 4 cis pi, we recognize where that is, that's over here, and we can convert that back to rectangular form. This one should be pretty easy, simply because it is straight to the left, so we can recognize that it is -4 plus 0i, or -4. DeMoivre's theorem can also be used for roots because we can rewrite roots as exponential fractions. So here we've got the cube root of I, and we're needing to go ahead and work that out and see if we can get an answer for it. You'll notice that means it is in rectangular form. So let's go ahead and put it into polar form to start with. Of course, I is simply right up here. It's just 1 up. A lot of people don't remember that, and for some reason, math students occasionally have difficulty with those that are just on an axis, but it's just 1 up. 1 up means that it is at a 90-degree angle, or pi over 2, and it's 1. So we're going to call it 1 cis pi over 2. And of course, it's raised to a power, and because it's the cube root of 3, that means it's raised to the 1/3 power. Hopefully you remember how to convert roots back and forth to exponents. So now that it's in polar form and raised to a power, we can go ahead and use DeMoivre's theorem. We're going to do it the exact same way. We're going to raise 1 to the 1/3 power. That means taking the cube root of 1. Hopefully you recognize the cube root of 1 is 1. And then we're going to multiply pi over 2 by 1/3. I'm not going to write it out because hopefully you can figure this out, that it's pi over 6. Once again, another great reason to use radians. Those fractions always work out. So we've got 1 cis pi over 6, and now we could go ahead and convert that back to rectangular form, and we will in just a moment. But for now, I want to show you one other really interesting thing. Let's just take this same number, the cube root of I. We could have written it as 1 cis pi over 2, but I want to show you something that may make a little bit of sense. We wrote it there, but if we went all the way around the circle and went back to that same spot, it would be the same cube root of I at that point. It would still be I. Only now it would have been written as 1 cis, instead of pi over 2, we would have added 2 pi to that. So instead of it simply being pi over 2, we added 2 pi, and it is 5 pi over 2. Of course, adding 4 pi over 2. That raised to the 1/3 power. We could do DeMoivre's theorem here as well. 1 raised to the 1/3, or the cube root of 1, comes out to 1 cis. And now if we multiply this by 1/3, we get 5 pi over 6. Now, that may not seem remarkable to you. You're like, okay, great, we just got another number. But here's the point. I want you to notice that right here, pi over 6 is a regular old angle. Pi over 6, first quadrant, regular old angle. But 5 pi over 6 is also a regular old angle. It's just in the second quadrant. The idea is that even by going all the way around the circle an extra 2 pi, one entire revolution around the circle, when we took the third root, we still got a regular angle that's between 0 and 2 pi. And the reason for that is because we're ultimately multiplying the final angle that we get by 1/3. And so we're dividing by 3, putting it back into the original 2 pi first turn around the circle. In fact, we could do this even one more time, go around the circle a second time, all the way around the circle. That would give us 1 cis, and once again we're adding 4 pi over 2, so we'll get 9 pi over 2. All of that raised to the 1/3. When we do DeMoivre's theorem here, we still get 1 cis, and now we multiply by 1/3, we get 9 pi over 6, and that can reduce down to 1 cis 3 pi over 2. So we have another answer here. In fact, as a general rule of thumb, when you're taking the roots of complex numbers, whatever root you are taking, in this case the third root, so we're raising everything to the 1/3, you will have that many possible roots. And these roots are 1 cis pi over 6, 1 cis 5 pi over 6, and 1 cis 3 pi over 2, which means we have 3 conversions to do in order to get this back to rectangular form. And so I'm going to do that on the next page, but I want you to understand that This whole process is made possible because you're actually dividing an angle. So you've got to remember to go all the way around the circle one more time, then do the process again. And you'll do that as many times as it takes to get all of the roots. So let's go ahead and take these three answers and get them back to rectangular form. So pi over 6 is in the first quadrant. Hopefully you recognize pi over 6 as a 30-degree angle. And of course we know this is 1. Once again, the way to get these values, the real and imaginary values, is simply to use our sine and cosine. So we're going to say the sine of pi over 6 is equal to the opposite, which is imaginary, over 1. Now, with it being 1, this is going to be easy because hopefully we can recognize that the imaginary portion here is simply the sine of that 30-degree angle. And of course, the real portion will be the cosine of that 30-degree angle. And so we can multiply this out and we get the real portion as square root of 3 over 2, and we get the imaginary portion as 1/2. And so we can just write it out exactly like this, and that is our first answer converted into the right form. So the second one, if we were to graph it out, we do the same thing. It's in the second quadrant. It is a 30-degree angle again. So we're going to have the same numbers. I hope you're not spending too much time writing out equations when you realize you've got the same number. Another 30-degree angle means we'll still get square root of 3 over 2 and 1/2. The problem is now we just got to check our signs. And obviously, with it going to the left, the real will be negative. It going up, the imaginary will be positive. And that will be our second one converted back. The third one's going to be a little bit different, simply because it is not a 30-degree angle, but hopefully you recognize 3 pi over 2 as a 270 degree. It's a quadrantal angle. It's going down 1. And once again, don't waste your time trying to figure out sine, cosine, and tangent when it's on one of the quadrants. You recognize that you just need to convert it back to rectangular form. It's going down 1, which means it is negative I. 0 real, negative 1 I. These are our three answers to this problem. Let's review very quickly how we got those answers. We first of all took our original function, the cube root of I. We converted it to polar form. We converted it to 1/6 pi over 2, recognizing that it was straight up and down. And then, instead of taking the cube root of it, we raised it to the 1/3. That's so we could use DeMoivre's theorem. We used DeMoivre's theorem by raising the 1 to the 1/3 power, which is 1, and then multiplying the angle by pi over 6. That's how we got our first answer. The other two answers we got because we went around the circle again. That raised that angle by 2 pi. So we just added 2 pi to the angle and then did DeMoivre's theorem one more time to get our second and third answer. After we did that, we converted them back to rectangular form. Before we do one last example problem, I want to show you something that might help you to save a little bit of time when doing roots using DeMoivre's theorem. If, like in that last problem, we were here at 90 degrees, or pi over 2, and we were finding a specific root, for instance, in last problem we were doing the third root, notice what was happening. We were taking our answer that we had gotten in the previous problem, and we were going back a step, adding 360 degrees, or 2 pi, and then dividing by that answer by 3. We're dividing that answer by 3. So we were adding 360 and then dividing our answer by 3. Which means that each time we were really, if we do this math out, we were really adding 120 degrees to the problem, to the answer, I should say. Because we were taking that 360 and then dividing by 3. Add 360 divided by 3 each time, adding 120. In fact, you'll notice where our answers were. They were here at pi over 6, 5 pi over 6. That's a difference of 120 degrees. And then our last one was here, another difference of 120 degrees. In other words, we were just rotating 120 degrees because we were adding 360 and then dividing by 3. If we were taking the fourth root, raising to the fourth power, well, we would have been adding 360 and then dividing by 4, which means each time we were adding 90. So if our first answer would have been here, our second answer would have simply been 90 degrees farther along. And then our next answer, 90 more degrees along. And then our last answer, 90 more degrees along. In other words, each time we don't have to go back, add 2 pi, and then divide again. We could just do that one time and take our answers. In other words, in the last problem, if we had, say, 1 cis pi over 6, we don't need to go through and add 360 and then divide by 3. Instead, we could just add 2 pi divided by 3 to each answer. Of course, 2 pi divided by 3, if we found our common denominator, would be 4 pi over 6. And notice pi over 6 plus 4 pi over 6 is equal to 5 pi over 6. And that was our second answer, 1 cis, 5 pi over 6. If we take that same 5 pi over 6 and add another 4 pi over 6, which is another 2 pi divided by 3, because we're taking the cube root, so we will add 360 or add 2 pi, then divide by 3. So when we add, we now get 9 pi over 6, which you may recognize reduces to 3 pi over 2, which was our next answer. Now we're going to use that to work this next problem, which may look a little more complicated, but knowing our shortcut, I think it will help out. So you'll notice, first of all, this one is already in polar form, which is nice because we can leave our answer in polar form as well. We're going to rewrite this so we can use DeMoivre's theorem as 32 cis 50 degrees. It's also in degrees. Some of you may think that's a little bit easier, but it's raised to the 1/5 power. So now we're going to do DeMoivre's theorem, which means we take that 32 and take the 5th root of 32. Hopefully, once again, you recognize this is really simple. They gave us a simple problem. The 5th root of 32 is 2. And now we're going to take that 50 and we're going to divide it by 5, or multiply by 1/5, and that of course will come out to 10 degrees. Now that's our first answer, and that's a really easy first answer. You'll notice it's a multiple of 10, it's nice and easy, perfect. But I hope you also recognize that because we're raising this to the 1/5 power, or taking the 5th root, we will get 5 answers. Each answer will come from going back to the original, adding 360, and then dividing by 5. Let's skip a step by go ahead and taking 360 and dividing by 5 and realizing that's what we're going to be adding to each answer. Hopefully you know, or at least you can use a calculator and find that 360 divided by 5 is 72 degrees, which means all of our other answers, after we found this, which by the way is called the principal root, all of our other answers will come from the same exact modulus, and then we will just add that number in. So this will be 82 degrees. Then we will get 2 cis, and once again, we're just adding 72 each time. So 152 degrees, or 154, excuse me, degrees. And then 2 cis, 226 degrees. And then our last one, 2 cis, 298 degrees. You'll notice if you add 72 again, we'll go over 360, and therefore it won't be a valid answer. So once again, to do DeMoivre's theorem, make sure you're in polar form. When you're in polar form, you can make sure you raise it to a power. Take the modulus, raise it to the power. Take the angle or the argument, multiply it by the power. And then to find all of your other roots, which is only necessary when you're actually doing roots, not just raising to a power, you will need to add 360 and divide by the number of roots to get your next value all the way through. And you'll get that many values. Hopefully this won't be too difficult for you. I want you to spend the rest of the class time working on numbers 1 through 15, just the odd problems. You'll get a chance to practice everything we've done today. You'll notice on numbers 11, 13, and 15, you get to leave your answer in polar form, so that'll save you a couple of steps.